what is a single point of failure? A single point of failure is a component or part of a system that if it fails, causes the entire system or critical function of the system to stop working. In other words, the failure of this single component will lead to the breakdown of the entire system, making it unavailable or in or make it failing like it's not usable anymore. So in highly available and reliable systems, avoiding a single point of failures is a key design consideration, because having a single point of failure that can bring down the system leads to vulnerabilities and downtime and service disruptions. And I would say is one of the biggest red flags in any system design interviews. So let's just to give an example of this one. Let's say that we have a client, okay? And this client sends a request to a server. And the server is communicating with a database. All of this system has multiple single point of failure. So right now we have one server. If this server went down, the client cannot request anything because we have only one server. So the client cannot get any data from the database. So a solution for this one is to have multiple is to have multiple servers. So when the client when one is down, the others can serve. And right now also we have another single point of failure, which is the database. We have only one database. If this one is failed, we cannot get any data. So to fix that, we can use like a master-slave database, so we can have multiple database instances. So if one is down, the others can serve. This is on high level how to solve common single point of failures. So as I said, examples of single point of failure, if we have a single server. So if your system relies on a single server, and that server crashes, the entire system will go down. If no backups or failover mechanisms are in place, the system becomes unavailable until the server is restored. Also database we talked about. So if your system depends on a single database instance and the database goes down, your application may lose access to crucial data. This can halt the system's functionality, such as processing transactions or retrieving user data. Also, if let's say that we are trying right now to fix that, and we will using a load balancer. If you don't know what is a load balancer, I created a video for that. So let's say that we have a client and we have multiple servers right now. We have server 1 and server 2, and we have master-slave databases. So we have database master, this one is master, and we have 2 slaves. And let's say that DB is slave 1 and slave 1 and DB slave 2. And in order the client to be able to communicate with the server or know which server to connect with, we will have to communicate with like a load balancer. Let me just delete this. So we will have like a load balancer. And we have the client here. The client will send the request, and the load balancer will redirect and distribute all the incoming requests to the servers. And we have a master-slave databases, and the servers will send the request to the database. So basically, the right request to go to the master-slave, any reader operations go to the slave databases. Also right now we have a single point of failure. We have a network or router, single point of failure. Currently we have one load balancer. So a single load balancer or network router, if not backed up by redundant system, can act as a single point of failure. If it fails, users won't be able to access the server behind it, leading to downtime. So to fix that, we can have multiple load balancer servers. Also, there is a power supply. So if there is only one power source or no backup guarantees or second power lines, it fails. So basically, if this system it fails on a specific location, let's say that in Berlin, Germany, and there is an earthquake happen in Berlin or something else happen in Berlin, that server might be destroyed. And to solve that, we use like multiple data centers. So we have like this one, it will be like a system called DE, and we will have the same system, for example, we put it in France, so if or another one in the US, and etc. There is and there is other thing, which is the application logic. So an application service or microservices that perform critical functions, but likes redundancy or backup instances, can be also a single point of failure. So if the service crashes or becomes unavailable, the whole system might stop functioning correctly. Let's talk about why is avoiding a single point of failure is quite important. The thing that we talk about is to increase the availability. So if you eliminate a single point of failure, your system become more reliable and available. Even if a component fails, the system can continue operating without interruptions. Also, fault tolerance, because designing systems without a single point of failures builds fault tolerance, meaning that the system can withstand failures and still function properly without affecting users. Also, it's great for scalability. Systems can redundant components can scale more easily. So single point of failure often become bottlenecks that limits scalability and create performance issue under heavy loads. How to eliminate the single point of failures? I would say we have one or two things. The first one is failover mechanism. I would say this is the most important thing, failover mechanism. Mechanisms. So active, or like there is active and passive failover. So you can have a backup systems that takes over in case the primary systems fails. This can be applied to servers, databases, or network components. Also, there is active failover, so both systems are actively working and can take over if one fails, providing better load distribution. I guess if you are familiar with how the Git hub or Git flows work, to have like a staging and production, or if you are into the production in AWS, you'll find there is something called a blue-green deployment. So you have two instances that is quite identical, and when you have a problem in one, for example, the green is failing and the green is a primary one, the green will be down and we'll use the blue instead. Also, there is something called redundancy. So there is a hardware redundancy, which will basically we use multiple servers, routers, storage devices, and power suppliers to ensure that failure of one component does not bring down the entire system. There is a software redundancy with deploy multiple instances of critical services or microservices, so that if one instance fails, others can take over. There is a database redundancy, implement database applications or clustering to avoid a single database instance. There is geographic redundancy, there is clustering, backup system monitoring, and alerts. There are multiple stuff that we might talk about, we will talk about in the upcoming videos, to talk about how to handle and how to eliminate a single point of failure. So in conclusion, single point of failure represent a major risk in the system design, as the failure of a single component can cause the entire system to become unavailable. Eliminating a single point of failure requires a thoughtful planning, and I would say, from my opinion, a single point of failure and knowing how to handle single point of failure operations is the best the best way to manage to success in your system design interviews. Because if your design have any single point of failure bottleneck, and when your interviewer asks you, for example, if we went to this system and your interviewer asks you about anything, like you have one load balancer and this is looks like a single point of failure, what should you do in it, and you don't have a clear answer for this one, it's a big red flag. It's really a big red flag, specifically if you are trying to be a mid to senior software engineer. So you have to know how to manage or how to handle every single point of failure. You have to know a lot of details in failover mechanism, redundancy, and like backup system clustering, etc. So that's it for this video, and see you in the future.